All right, I want to just welcome everyone to the SF CloudOps meetup. Thank you for coming tonight. Just want to, if you want to tweet about the event, anything good you hear, these are the hashtags that we like to see. So feel free to put something out there about SF CloudOps. Tonight, just want to give you the requisite, who we are. We're Lithium. We do social CRM. We do community really well. We're doing some really cool, fun stuff. That's why we get to meet people like Armand. I saw Mitchell's here tonight as well. We've been able to really try to bring these back into things that we've learned. We really try to bring in some of these speakers that have helped us, whether we use their tool or not. We found that they've really helped shape our vision about what we're trying to do here at Lithium with, things you hear about hybrid cloud. You hear, trying to mix these environments. And you find out when you really dig into the details, it's a challenge. So really appreciate the opportunity to kind of work with it. And if you'd like to learn more about joining Lithium, we do have some opportunities here. And I'm going to just invite up Tara real quick. She's going to talk about some immediate opportunities. We'll keep it brief, but just let you know what we have available.
Hey, everybody. How many of you were here for our Skybase meetup? Any of you here for that? Ooh, new crowd. Okay, so we're working on hybrid cloud application deployment systems. If you had been here, you would know about it. We'll be open sourcing it hopefully in the next month or two in a beta sort of form. We're looking for people who are interested in working on this platform. The job invite will go out soon. If you're remotely interested, just come find me by the bar and I'll give you a drink and we can talk about it.
She does make good drinks. I appreciate that. Yes. So with that, I really want to, I'm excited about tonight's presentation because, for us, we use AWS a lot. We know CloudFormation a lot, the good and the bad, and I'm sure a lot of you guys probably know that as well. So there was one feature that when I heard about Terraform, I was like, first off, these guys are really kind of close to how we think. And then there were some features in here that we were like, wow, that kind of speaks to what we're trying to get accomplished. So that's why we wanted to invite up Armand Dadgar. Have you ever been in a data center before in your life at all? You have. All right. I was wondering. That was a debate. We were debating, has he even been in a data center? Because there's this new generation that we even wonder, they're not like the old school crusty guys or the neckbeards. These are guys who are new school doing cool stuff. So with that, I want to invite up Armand, and he's going to talk about automating infrastructure with Terraform.
Awesome. It's seeing my laptop sees the other display. I don't know. It's not picking it up. Let's see. Cool. Awesome. The colors are a bit off. Whatever. Awesome. So thanks a lot to Joe and Lithium for hosting this. I'm pretty excited to be here and talk to you guys today about Terraform. Lithium's a pretty awesome use case. As they said, they have a pretty complex hybrid cloud scenario, and so today we're going to be talking about what it's like to do orchestration at cloud scale. For those of you who don't know me, my name's Armand. I'm everywhere on the internet as also just Armand, and I work at HashiCorp. So we are a DevOps tooling company, and we're basically working on getting towards a software-managed data center. Some of our tools you might recognize, we make Vagrant, Packer, Surf Console, and Terraform, which is what we're going to talk about today. So just as an overview, what we're going to be talking about is, one is kind of what is orchestration, because this term is thrown around a lot these days, and it's kind of become a little bit meaningless. So in the context of this talk, I want to frame what we're talking about here. And then we're going to go through kind of the origin story of orchestration and how we've ended up with the current modern-day data center, and kind of where we're moving towards with the next generation cloud scale data centers. So the first question is, what is orchestration? This term, super overloaded. It could mean anything from booting an AWS instance to running Puppet. But for the purposes of this talk, what we're concerned about is basically infrastructure lifecycle management. And so there's kind of a fixed relationship here, which is the first step is really acquiring the resource. So resource acquisition. Once you've acquired the resource, how do you go about provisioning it? Whether it's a switch, whether it's a server, whether it's a logical record like a DNS entry. How do we set that thing up? How do we update it, need be? And when the life cycle is over and we no longer need that resource, how do we destroy it? So for our purpose, this is the life cycle we're going to be talking about. So where did we start? We started with this guy. So at some point, maybe, you started a startup and you only had 5 users and this is where you started, or 20 years ago, this was state of the art. We had one server. There was only one to rule them all up. And when there's changes, you just go in there and just like fiddle the bits. But at some point, you reach kind of the more than one scale. You reach the, okay, now we have racks. Now it's more of an issue. We have to think about these things. And this is kind of not that long ago. The data center of yore is people still run this. And in this world, acquisition time is like on the order of weeks. This is something you have to think about. You're calling Dell, you're calling HP, and you're like, please send me 20 servers, and then you wait. And those servers come, and you rack them, and that's manual. And then people start SSHing, and that's manual. And pretty much every process of it is you're calling a sysadmin or you're calling someone. There's just a lot of calling involved. And you have to manually get things set up. But right around 2006, there was a tectonic shift, basically, which was the cloud. Or less ambiguously, what I'm going to refer to as elastic compute. So elastic compute really is a specialization of labor, right? What it's saying is, I'm a software company. Why am I in the business of running a data center? I don't know anything about networking. I don't know anything about power and AC units. I really shouldn't specialize in building and managing my own data center. Instead, someone else should specialize, and they should be a utility company. So really, elastic compute lets us think about computing as an on-demand utility. It's cheap, it's on-demand, it's unlimited in nature, and it's elastic, right? One of the nice benefits of this, though, is because we have people like physically mail something to us, we move from months or weeks of acquisition down to minutes, right? Just make an API call, and 60 seconds later, you have an EC2 instance. So this is a huge shift, right? The other shift is basically we move from a CapEx model of spending, where you have to spend $1 million to get that initial data center, into you're sending 2 cents an hour, right? It's a totally different world. And what this does is it basically reduces the barrier to enables a lot of innovation to be done in a SaaS kind of a model. So now, if you want to start a startup, you need a $25 AWS credit, you spin up some instances, right? And you can take that risk on building, the next generation SaaS to do DNS or a CDN or whatever it is. So this enables a lot of innovation. So very quickly, we see basically the beginnings of the cloud wars, right? Amazon got here first. And what's great about this is it's a race to the bottom, right? All of us benefit because we get more features, we get it at lower cost, and we get higher reliability. The only problem is now we have to deal with, okay, am I going to use 17 different clouds now? And this is kind of a nightmare. Very quickly, enterprises also figured out that, hey, there's something to this elastic model. So we see basically the rise of an on-premise cloud solutions as well. So mostly, this is companies still willing to front the capital expenditure costs. You still have to go out and spend $10 million on the hardware, and then another $20 million on VMware. But basically, you get the nicety of having a cloud, and you have that elastic on-demand API-driven nature. And so really, we're able to now move into this world where our acquisition time for new resources is on the order of minutes, right? So now the question becomes, okay, great, we can spin these servers up left and right, but how are we provisioning them, right? That's kind of the next logical step once we have them. And so again, as we talked about in the early days, it was like, well, you had the one server, you plugged in your keyboard, maybe you had a CRT monitor, you started manually doing it. At some point, you had a sysadmin who decided Bash and Perl were the way to go, but they were the knowledge silos. There was 1 or 2 of these guys. They knew the magic incantations to get the Perl script to like self-evaluate its regex and do things. Luckily, right around the same time as elastic compute, we see the rise of config management. So now there's probably also more that I'm forgetting about, but Chef, Puppet, Salt, Ansible, and they allow us to think about provisioning at a higher level of abstraction. So instead of writing shellcode or Perl to whatever operating system and version we have, it's a higher level abstraction of, I just need this file here with this permissions. But more than this abstraction, it lets us codify knowledge. So before you had that sysadmin guy who knew what that Perl script did and nobody else, but now we're able to move that knowledge of that guy into shared Chef repos or Puppet repos and codify their knowledge and share it across the organization. So one benefit of this is great. Now anyone can just go in there and look and be like, how did this file get here? How do we set up a web server? How did the pieces come together? So from a knowledge sharing perspective, it's great. But because it's code, like it's an executable representation, we're able to use it to automate. So Chef and Puppet, one of their beauties is that it's much faster than running that Puppet thing. It's less error prone because it's totally automated. On the horizon, basically, it's maturing rapidly is containerization. It's solving a similar kind of problem around provisioning, which is how do I do OS agnostic packaging and simplify my application delivery, right? You don't want to have to think, do I need a Debian, or do I need a Deb or an RPM package or whatever Gentoo uses? Instead, you just containerize it, deliver it to a Linux thing, and it works alongside your existing config management tooling. You just spin up your container, run Chef inside of it, package it, you're ready to go. So it kind of brings us to this world, where now we're able to rapidly acquire new resources and then run our config management tooling and basically pump out very quickly new resources that we're able to acquire and provision reliably. So now we're doing things basically better, faster, and cheaper than ever before. But really, we want to get to this world of like wu-wei, doing without action. Because the only thing better than doing it better, faster, and cheaper is not doing it at all, right? So because of all of this SaaS innovation enabled by elastic compute, we've seen all of these great services showing up. Now, nobody really runs their own CDN or DNS or email or payment servers. Instead, we use a SaaS for all of these systems. And we outsource all of these things that aren't our core competency to these SaaS providers. Because why do you want to manage your own email delivery, right? And what it allows us to do as software companies is we get to specialize on what our value add is. Because realistically, unless you're Google, no one's value add is infrastructure. And so we're seeing this huge diversity now in basically the SaaS world, right? This is just a short list of a few different kind of problem spaces, but you could go down and for every possible category, there's probably a dozen competent SaaS providers. So there's a huge diversity, there's a huge competition, and we all win. Because we're moving more efficiently, there's less stuff to maintain. But as operators, we now have to deal with the complexity of the fact that we're running all of these different SaaSes as part of our infrastructure. Instead of there being a consolidation and like a reduction in complexity, we're rapidly approaching this in terms of what it's like to run our data centers. This complexity is just rising, and it's not going to go away because it just makes sense. You're never going to move things in-house when it's more expensive and more difficult for you to do so. So the modern data center really is very different than that picture of the racks sitting in one room. Now, you're basically, it's common for us to see hybrid deploys of you have physical hardware that's running an on-premise cloud like OpenStack that is VPN'd into public clouds. And these are globally distributed in nature, right? So you're not managing one room anymore. You're managing 3+ data centers across the world. And you have a matrix of different provisioning systems used for each of them. You're probably still hand configuring the physical boxes from 20 years ago. You have some Chef, you have some Puppet, maybe there's a cluster running Docker, but it's not standardized. Things just kind of layer just like that tower. And on top of all of this, you have integrated use of PaaS and SaaS throughout the organization in a non-unified fashion. And so really, as operators, it's overwhelming. It's like, how are we supposed to deal with the fact that this complexity is just bubbling out of control? Because the role of an operator really is kind of three things, right? The first is to truly understand the infrastructure. Because when something goes wrong, they're the first line of defense. They're the ones who have to be like, okay, what's happening? Is BGP broken? Did we lose a core switch, right? And so you have to really be able to understand your infrastructure at a deep level to be able to diagnose it. The next is you have to be able to adopt new technology and stay nimble, right? Because we're seeing all of this SaaS innovation, you have to move faster than ever before, basically, to stay relevant in this world. It almost doesn't matter how big a company is. You talk to them, they're worried about being irrelevant in 5 years. So you have to be willing to adopt new technology and move quickly to stay relevant. And part of this is you have to be able to deploy applications efficiently. So really, what an operator wants to do is move fast without breaking things, basically. And so to that end, a tool that we've developed at HashiCorp is Terraform. And so we had a number of goals when developing Terraform. We basically wanted a single workflow to unify any of the underlying technology, and so we need to be able to support and represent that. And part of this is really treating SaaS and PaaS as a first-class entity in the data center. They're not going away, and they're only going to proliferate. So how do we pull them into the fold and pull them into the management infrastructure in a way that operators can use and understand, basically? And so really all of this comes down to the operators. How do we put them first? How do we make sure they understand this and can continue to scale the data center? And so one of the first kind of principles behind Terraform is infrastructure should be code, right? In the same way that config management brought codification of knowledge, we wanted to pull that into the infrastructure layer, right? We want you to be able to describe our desired state and simply let Terraform get us from state to state prime, as opposed to having to figure out on a complex infrastructure how to get there ourselves as operators. So we want the management of our data center to be automated via Terraform without us telling it the how, just the what. And again, like I mentioned, a fallout of this is anytime you want to know what your infrastructure looks like, you just look at the Terraform configuration because it's fully documented. The documentation is executable. And you also get the same knowledge sharing that you got with config management. Once one person in your organization describes how to set up and scale a 50-node Redis cluster, right? Because we have to be able to represent the entire data center for this tool to really be useful. If you had to use multiple different tools and piece together your representation, it wouldn't be useful because you're going to fragment your knowledge. Parts of it won't stay up to date, and you'll end up kind of losing consistency with what your infrastructure actually looks like. So again, this means SaaS and PaaS had to be in there. It means we can't just deal with compute. To be able to deal with networks, we have to deal with storage. You have to think about switches and routers as first-class elements of your data center. And so to that end, HashiCorp introduced a new language. We call it HCL, the HashiCorp config language. It's heavily based off of libucl, so it's not totally out of the blue. And its goals were basically twofold. One is that it should be human readable, because most of the time it's going to be humans that are looking at configuration being like, what's wrong, or how does this work, or how do we go from A to B, right? Very little of the time is spent by the computers reading these files, and they're so incredibly fast that you don't need to optimize for their parse speed. If you do want the computers to be able to automatically generate configuration, and you want to parameterize in a way that's more complex and more organizational specific, the tooling is also JSON interoperable, which makes it easy for automated tooling to push things in and out of Terraform. So this is a little example, basically, of what Terraform HCL looks like. Let's see. So kind of this first block here, I just want to unpack it a little bit. It defines a resource. So in Terraform's world, a resource is basically anything that can be represented. And so it has two parts. You have a type, and you have a logical name. So in this case, DigitalOcean Droplet is specifying that the type of this resource is the instance of compute in the DigitalOcean kind of infrastructure as a service world. And we're just going to logically name it web. And then we give it some parameters that describe kind of the minimum necessary for DigitalOcean to be able to boot this instance. So here we're saying it's a small size instance running CentOS in the SFO data center. And then here we're defining a separate resource in a totally different kind of model of the world. So DNS Simple is a software as a service DNS provider. Right? Sorry, I guess this side makes more sense. So they're a software as a service DNS provider. We're just going to assign this record the logical name of hello. And basically, we want to define an A record such that the IP address is actually populated with the DigitalOcean instance. So this is a really powerful concept if you think about it for a moment. What we are saying is we have a software as a service that we're a subscriber to, but we're going to spin up an actual infrastructure node, get its IP address, and create a DNS record based off of that, right? And we're codifying all of this in a way that otherwise you're going to have a Perl script somewhere that's like, okay, spin up the thing, then parse the response, get it, and then go ahead and make this request, and you have 2,000 lines of indecipherable Perl, and you're like, what is this doing? Versus this, you're like, oh, spin up the thing, take its IP address, create a DNS record, right? It's instantly obvious. You didn't have to go through 2,000 lines of code to figure that out. And so part of this is that Terraform uses this to do dependency management for you. So as an operator, you don't have to figure out, does the DNS record come first, or does the droplet come first? By maintaining a resource graph and understanding the dependencies between them, Terraform automatically handles the ordering of operations. It can automatically parallelize operations that aren't dependent on each other, and it lets us visualize what this actually looks like. So as an example, here's Terraform being asked to visualize what that toy infrastructure looks like. And what it's able to represent is that we have this droplet. It depends on basically the DigitalOcean provider, so it has to be able to properly authenticate and have the API tokens there. And then we have a DNS Simple record, which depends both on DNS Simple, but also that the droplet must exist first, right? And so this notion of basically Providers is what's the key to allowing Terraform to interface with all sorts of external systems. The providers, in essence, are the integration points between Terraform and the rest of the world. They expose different resources. So what we saw before was the DigitalOcean one had the droplet resource. DNS Simple has a record, but both of them export a few other also resources that we can make use of. And for each resource, the provider implements a simple CRUD API. This then creates the separation between Terraform core and the provider. The core then can handle all of the actual logic of parsing the files, understanding the dependency flow, ordering, parallelization, error handling. All of that gets offloaded to the core. And really, to integrate new systems, you're writing a very thin CRUD layer against a REST API. And because of this kind of notion of having multiple providers that can be independent on each other, it allows Terraform to kind of understand the infrastructure in kind of a layer cake approach. I use this analogy a lot more than my coworkers appreciate, but I just like cake a lot more than they do. So in Terraform's world, you basically have a provider that understands the level of your infrastructure, and they're orchestrated kind of in the order that logically makes sense. So for example, you might start at a physical level, and you need to provision that up into a managed cluster. And you can think of kind of, the OpenStack has like a thin dividing layer, right? There's the layer above the API and the layer below it. So below that layer, Terraform is booting and provisioning and installing OpenStack. But above that layer, you're OpenStack API to start virtual machines, right? It's a different kind of a workflow. But then you're bringing up virtual machines, and maybe above that, you're loading on a containerized workload. And at each of these levels, Terraform is able to use the appropriate provisioners in the correct order, such that to go from basically physical hardware all the way to virtualized containerized workload is a single Terraform apply command. So it's great and all that we can do this and start from physical and go up to the container, but relatively speaking, the initial construction, you can hard code it and probably get away with it and reason about the ordering. Where things get changes, right? If you want to change something in a complex infrastructure, there's all sorts of intricate interdependencies that have to be captured and handled, right? If you want to change the version of your web server, do you need to update the load balancer? Does the load balancer's DNS record need to be updated? Do you have to notify Cloudflare to do a CDN invalidation, right? All of these things are interconnected in a way that becomes very hard to reason about once you're running hundreds of nodes, maybe tens of apps, tons of SaaSes, right? And so as an operator, when you're like, okay, I want to make this change, there's kind of like, what's going to happen right now? Like, I'm going to change something, but what do I expect to be the result of this? And basically, Terraform acknowledges that it's very hard to divine basically what changes are going to take place. Like, what is the butterfly effect of any given change? And so we take kind of a measure twice, cut once approach to the problem, which is, how can we make it clear to an operator before we do something what we're going to do so they can fully understand the implications of changing something? If it's clear, oh, okay, changing this value is going to cause this resource to have to be destroyed and recreated, maybe you want to rethink how you're going to do that update, and you're like, actually, I don't want to destroy every web server. And so the Terraform approach to this is basically to separate the planning phase from the actual execution phase, and to do this in a very strict way. So Terraform actually doesn't allow anything to be executed, so to speak, until it's been pre-planned. And once that plan is finalized, it strictly executes only what's in the plan. This is a pretty big departure from things like CloudFormation, which don't make that separation, and you figure out what it did after it did it, which maybe you want it to do, but maybe is not. So that model of kind of how Terraform operates is it kind of examines the existing state of the world along with your desired configuration and forms its execution plan. The execution plan can then be visualized in the same way. Terraform can tell you what it's going to change, what it's going to destroy, what it's going to create. You can inspect it and be like, this looks great, and then pass it through to its plan application phase, and it can move you from state to state prime. You can also abort it at that point and be like, no, this plan doesn't look right, and tweak your configuration until you get it to do what you want it to do. So kind of an overview, Terraform has a few big tenets behind its design. One is that infrastructure should be code, that this gives us understandability, it gives us documentation that's always up to date. It lets us compose providers in a way that we can kind of express this layer cake leveling of our infrastructure but it also lets us merge in software as a service like platform as a service like Heroku, and merge that in with our infrastructure as a service like AWS. And because of its separation of the execution and application phase and the resource graph, it's able to safely iterate on that. So we're able to make changes in the right order and be confident that it's going to do exactly what we expect it to do without it being like, oops, I accidentally blew away my load balancer. And because of its very technology agnostic provider model, it doesn't lock you into anything. You know, you can build your whole thing on AWS. Tomorrow there's a brand new infrastructure as a service. You're like, great, I want to migrate to that. You add that provider gets implemented, and now you have a migration path forward. So it future-proofs you against technological change because its model isn't specific to any particular technology or vendor. So as an operator, these are awesome features to have, right? You get a unified configuration that's able to describe your infrastructure end-to-end at every level of abstraction. You also get an atlas for your infrastructure so that when the main kind of DevOps guy leaves and you're like, oh God, how does anything work? You just open up the files and you're like, oh, okay, this is how everything connects. These are how the pieces come together. These are the dependency chains. And you kind of only have one tool to deal with to do all of this. You're not first running one tool to boot your AWS and then running a separate tool to run your provisioner and then a third tool to update your load balancer and a fourth tool to update your DNS records under one umbrella, one command. And we already talked about how it's future-proof. But its uses kind of also keep going past operators. You can basically extend Terraform to actually help end users as well. So in this case, the end users are your developers, basically. So if you kind of have a central ops team that's responsible for maintaining and babysitting the infrastructure itself, well, then you have your developers who are responsible for developing the applications. And what you'd like to be able to move to is kind of a self-serve model, so that as operations people, you're not responsible for every application level change or deploy. You just want to make sure, the substrate is ready to serve, and the applications can be deployed by the development teams independently so that you can move a lot more quickly without bottlenecking on a central ops team. So when you move to the self-serve model, you really need to basically be able to decompose your infrastructure into its various layers and then delegate it to the appropriate team so that your deploys can be happening in parallel. So in this, going back to the previous example, stack level resources, they get to just treat it as an elastic internal cloud, right? Extending the separation further and allowing kind of the operator and user interaction is a notion of modules. So a module lets you think about your in terms of its abstract components. So you don't have to think about your Redis cluster as being the Redis nodes plus the Redis sharding layer plus the monitoring systems. You just think about it as, I have a Redis cluster. And so it allows you to think about your infrastructure at a higher level of reasoning in the same way that Chef and Puppet allowed you to think about throwing files on disk at a higher level of reasoning. And it also lets you reuse that configuration across your organization. Likely, you probably have multiple projects within an organization that need to make use of a cache. You don't need to refigure out per team how to configure and scale my memcache or Redis. You can have a single configuration that takes variables, and then you share that across your org. So for an operator who's basically writing and developing these modules, they want to be able to treat it like any other Terraform resource. They're like, I'm going to write a console module such that the organization can make use of console. They just have to require it. And to them, basically, Terraform can show them this unpacked white box view of it where they care about the intricate details of what's happening inside of that box. But as an end user developing their service, they maybe don't care. They just say, hey, I have this instance, and I just need a console cluster running. But I don't care about the details of how you do it. Just n equals 3, and you deal with the details of bringing up, managing that, making sure the whole orchestration flow works. I just want to pull out the IP address of a console node. So this kind of helps us move towards this model of cloud scale infrastructure, right? Reaching certain organizational sizes, you have a very complex infrastructure, right? It's no longer 12 nodes running in the basement. There's thousands of machines running tons of different layers of technology across the provisioning matrix. And this infrastructure is fundamentally shared among the organization. Your own cloud for every dev team, right? And so you end up with this weird dichotomy between dev and ops. You usually have your central ops team, ability, performance, they care about security, and then you have your developers who aren't as concerned about a lot of these things. They just need to deploy their bug fix because it's 2 in the morning and the app is down, right? So they want to be able to move fast. And they're doing a decentralized deploy model, right? dev team. There's probably one dev team per internal tool or application, so they're not coordinating with each other. So you want to move to this continuous delivery model, and the operations people really are the front line of enabling that. So how do we reduce the friction, basically, between these two teams? How do we reduce kind of the throwing over the fence between dev and ops and kind of make this easier? Well, self-serve is kind of that answer. The operations people provide the self-serve portals, the developers simply consume it, right? And you want to do it in a way that when you're ready for change, right? So when you want to change underlying technology, you're not having to change the workflow all the way from operators clear through developers, right? And so Terraform kind of offers a pipeline way of doing this, as we talked about. You can split the interactions with Terraform and delegate the work kind of appropriately to each team and manage the layer cake in each layer. So the operations maintain the underlying substrate. Maybe they're responsible for writing the modules and making sure that they're tested and scalable. And then your developers treat it more of as a black box plug-and-play system, right? They pull in the modules they need, they allocate and provision the resources they want, but they don't really care about maintaining the substrate of like the VPN and the broader networking and storage and configuration of the data center as a whole. And so together, by using this one pipeline, the two teams are able to kind of move fast without breaking things, because they make sure Terraform is there to enforce the constraints and make sure nothing crazy is happening. So kind of in conclusion, Terraform offers a one tool to unify them all, so to speak. And it's really there to enable operators, but by doing that, we're enabling end users as well by making kind of the self-serve model possible. And by being able to pull all of it under a unified language and a unified workflow, we're kind of able to tame the complexity of the data center and bring all of these PaaSes and SaaSes and IaaSes under one giant umbrella. So, if you guys have any questions? No, so you can't safely do rollback with a lot of infrastructure. So what it does is, because it's able to figure out what are the dependent resources, if there's an error applying a particular operation, any of the dependent operations subsequent to that won't be executed, right, because you've hit an error state. But the other changes that are not affected, so to speak, the ones that can happen in parallel, Terraform will allow those to continue. And when it's done, when that tree of operations is done, it'll be like, this web server failed to provision, Puppet reported exit code 1. We've marked this resource as being tainted. And so it won't go ahead and destroy it because of that strict plan enforcement I talked about before. Because Terraform promised you, I'm going to boot a web server. It didn't promise you I'm going to boot it and then maybe destroy it. So what it'll do is it'll say, I've made it, it's tainted. Next time you try and do an operation, I'm planning on destroying this. So the next plan and the next execution will kind of handle that cleanup. But because of its model of a strict execution, it won't attempt a rollback because it's not something an operator anticipated. Yep. Yep. So it's like if you're getting a temporary error, you. Uh-huh. Yeah, we've thought about this. The problem is there's a large graveyard of people who have tried to basically abstract away the semantic differences, right? Because it's like, from a distance, they kind of look the same. Start looking closely, there's enough gotchas that it becomes very challenging to do it, right? And it's usually not the general. It's kind of, once you start getting close to the edge boundaries, that's where it's hard to mask the differences. So it is possible in the very general case, but as you start getting more specific, where it's like, oh, I need an IPv6 address, and this particular provider only does IPv4. Well, now it becomes very challenging to mask the semantic difference. So right now, Terraform doesn't make an attempt to mask that. It exposes the semantics all the way through, because you're like, this is very clearly a DigitalOcean droplet type. It's not a general purpose compute thingy, right? So right now, we don't make that approach. It's, of course, possible to build meta tooling such that you're just generating Terraform, where you're like, generate me a DO-specific configuration or an AWS-specific configuration, and then you could emit the proper Terraform code to do that, as long as you know within your domain that those kind of edge cases won't bite you, if that makes sense.
Kind of a follow-up question to that. Instead of generating Terraform code or the JSON that would be fed into Terraform, could I define a resource type that then, I guess, kind of calls out to the Terraform DigitalOcean resource or the Terraform AWS instance resource? Like if I know that I
Right.
need IPv4 and image types.
So you're saying make a magical provider that basically underneath just shims out to the right level.
Because in your own, yeah, exactly.
Mhm.
In my own infrastructure, I know the differences that I care about between those providers.
Right.
And I know, and generally I'm going to probably be using kind of a least common denominator among them. And so find my own resource type that
Mhm. So if it's a question of theoretical possibility, then you could. You certainly could, right? It's just doing RPC calls. Whether or not you'd want to, may be a different question.
so in order, like,
It's possible. It's possible. I won't say no.
Terraform doesn't make it easy, but I could RPC out to the underlying.
You could, yeah, basically. You could just forward the request to DigitalOcean and then pass through the result. Just lie to Terraform Core and it wouldn't be able to tell.
You mentioned the thing about tainting a resource.
Mhm.
That sounds like it understands purging. Really good purge resources it doesn't know about.
Well, because the provider is required to provide the whole CRUD cycle, so it tries the create, and suppose the create fails, then it knows later I can come around and call delete and basically go back to like fully resetting that particular instance.
Okay. So if we made Terraform and we had a definition for an instance to say it's 2x large and we change it to 3x large.
Mhm.
You can't just like change that. So it's gonna like make one and then on the next one it'll delete.
So it depends. So some providers allow you to do a rescale. So like in DigitalOcean's case, it will actually snapshot and resize the machine. But in AWS's case, it will have to do one of two things, which is either create the new one and then destroy the old one, or create a new one. I might have just said the same thing twice. Create a new one, destroy the old one, or destroy the old one, create a new one. Basically, it'll have to replace it.
On the same path.
On the same, sorry?
On the same Terraform apply.
Right. So when you run the plan, it'll tell you that basically it plans to do a create destroy operation. So it's going to create and then destroy the existing instance.
In those situations where it's not going to do a create destroy,
Mhm.
how does it know what's left over that's tainted? How does it store the state of what's tainted and save and delete?
Okay. So Terraform is stateful itself. So Terraform maintains a state file. So once you run apply, it basically emits a. This is the current state of the world. You can run Terraform Refresh, where it's like, okay, I'm going to look out, query AWS's API, see, is this still the state of the world? So it basically has a way to reconcile its view of the world with what the underlying providers think the state of the world is. But yeah, it uses its own state to track this. So it'll mark that particular instance ID as being tainted in its state file. Yeah.
Just as a follow-up to that, do you generally recommend that you like check that state into Git, or how do you deal with Terraform?
Yeah, that's a great question. So right now we recommend checking it into Git. We're working on a way to avoid this by just being able to like easily tell Terraform to like materialize my state when I need it, and then push it to a state store when you're done, and then just pull it back down anytime you're about to do an operation. So we want to move towards a world where the state file can be treated as being a little bit more ephemeral, because you don't want to lose it, but it's in transit, basically.
So follow up also, when I found Terraform, I was also evaluating CloudFormation because I've been evaluating it for a year and decided no, because we're multi-cloud.
Right.
And on-prem that we have that. But one of the on-ramp or onboarding tools to get into CloudFormation is CloudFormer, and
Mhm.
I was wondering if there's some way for Terraform to do a similar thing. I think you almost hinted at it, to basically discover the current state of something out there in the cloud if we can target it towards those things.
Yeah, so we're working on a recovery tool to be able to do this. One of the blockers was that the state store was kind of in a binary format up to 0, 2, and so it's moving to a more human editable format. And so the idea is there'll be a separate tool from Terraform. They'll be able to basically, it'll act like the CloudFormer. So it just queries AWS and generates Terraform's state file. So it bootstraps you into the Terraform world. It covers most of AWS right now. Yeah, I think there's like some of the weird edge ones, but they're being added all the time. I don't actually know what the current status is, but it's pretty close. Oh, Mitchell might know. Right. Right. Yeah. So it kind of goes back to the same, almost the same question he had with the state store stuff. So we're looking at basically being able to use a centralized repo, almost like Git, to be able to pull in and out for that. Yeah. Yeah, we're working on basically making the environment like a first-class thing for the state file. So it'll be clear, like, are you sure you want to nuke production? You'd be like, no. Oh, sorry, I ignored the side. Go for it. Mhm. Yeah, so it goes back to that Terraform refresh I was talking about. So when it builds that state file, it's kind of its view of the world right when it ran the apply. So assume you don't run apply for like a week and like whatever 5 nodes fail in AWS. The next time you run a refresh, basically, and refresh runs by default anytime you run a planning phase. So anytime your Terraform starts planning what it's going to do, it checks what the world is. It'll notice that, oh, whoops, these 5 web servers I thought were running are actually dead. So its plan will be to recreate those 5 that have died. So it'll kind of catch that drift that's occurred while it hasn't been running. You could do something like that if you were seeing a lot of drift, but like typically infrastructure doesn't drift fast enough for that to really be an issue usually. Because you're not losing machines, hopefully, every 30 minutes. You totally could just put it on a cron and just run refresh and email me anytime you're seeing like drift from the last state. So you could do that. Right. Right. And so probably what would end up, that would expose itself as an error during the apply, and the Terraform will be like, whoops, I thought this node existed, I tried to do something, AWS said it doesn't exist. So then that dependent update will fail. The next time you run plan, it'll be like, oh, actually the node doesn't even exist anymore. Let's do a recreate and then continue the next time. It kind of is built into the model because it catches the error and then you just do another refresh plan cycle. So then the next time you run it, it's able to account for the drift. So it'd be, because accounting for it during the apply would mean we'd break our strict planning. Because our plan has said we're going to do an update, and then if we detect it doesn't exist and try and do a create, then it means we did something that we didn't tell the operator about, right? And so we shy away from doing anything in that vein just because it makes it very hard as an operator at large scale to reason about what it's about to happen. So we're very strict about, if we say we're going to do an update, try the update. If it fails, don't try anything else. Like, don't try a create. So, but it naturally fits into you just do the whole cycle of refresh, plan, apply again, which really is all kind of like built in to just apply, right, with the right flag. So you just run Terraform apply again. It'll do the right thing, but it'll do what it promised you. Oh. It depends on your definition of strictly doing what it said, because it's like an idempotent delete at that point. It's like it promised it would delete, but it doesn't exist, so it deleted, right? We did a few of the handful ones for the launch, but since then a lot of them have just been pull requests. People have just been adding features in. So it's kind of a mix. We do some of them like as we have a need, and then other people as they have needs, they pull it in. It's kind of mixed.
So, thinking through the development engineering pieces and looking at the operations groups, I just wanted to try plus one is abstract.
Mhm.
Structure, because I could see us trying to say, all right, well, your environment's got database server, Redis, and two application servers, and on my development machine, it's vagrant instances. On my deployed environment, it's AWS, but on production, it's VMware. And I want to keep the same frame, but just change like the underlying provider for a host, right?
Yeah, totally.
Today, we actually have to go in and change the providers and basically make 3 sets of plans, right?
Right. Yeah, exactly. Yeah, it's definitely a limitation we're aware of, and we think about it. That's why I knew right away. I'm like, yeah, this one has issues because we think about this one a lot. Yeah, we're thinking about it. That one is a little backward compatibility-wise than the state file because it's very ephemeral. So we're probably not in 0.3, but we're talking about the plan file as well. That one's easier to change in the future because it only exists for that short period between plan and apply. So you're not checking it in or really like persisting it long term.
What about auto scaling from the perspective of like bootstrapping in a new server as well as, if you have a plan that says there was 4 servers and now there's 5 because of the scale,
Mm-hmm.
how does it deal with that?
Yeah, that's a great question. So basically there's some meta parameters that Terraform treats magically. So you can define a resource as having like some number of occurrences of that resource. And you can actually just make that a variable and then change it. So you can say, count of my web servers is 4, change the variable through whatever an environment flag or something, go to 5, and then the next time you're in Terraform, it just does a create. So it'll figure out, into Amazon's auto scale model, that you can just say, I have one instance of auto scaler. It has min 1, max 50, and just let Amazon deal with it. Or you can move that to Terraform and say, like, I have web server, count is 5, and then change count later to 10, and Terraform will manage that for you. So it's up to you. If you want to use the auto scaling stuff, that's built in. But if you want to auto scale something that isn't maybe like an EC2 instance, then you have that opportunity to do that in Terraform as well. But again, it just depends. If it's something where you're happy and you like the kind of always-on nature of Amazon's auto scaler, then you can just represent that as well. Mm-hmm. You could, so the way Docker would be treated basically on Terraform is Terraform draws a very, very clear boundary from being a scheduler. So Terraform is not an application scheduler. It's not in the world of Mesos or Kubernetes. So what you could do is if you're saying, on this machine, I want count 4 Docker containers, it can totally do that because that is a static acquire provision kind of a problem that fits in Terraform's world. It's not a dynamic problem of, I want 4 of these containers living on any one of my instances, because then you're in the world of scheduling, which is not a problem Terraform handles. It just runs at a different granularity, and it draws a very clear boundary there. So if it's like, I have 4 cores, my Node.js app is single-threaded, I just need count equal 4 because I know I have 4 cores, that is something that fits in Terraform's model. If it's, I need count 4,000, and it has to just be somewhere on my cluster of 10,000, that doesn't fall in Terraform's world anymore. Yeah, it would be a Docker provider. Yeah.
This actually mentions something I haven't seen yet, which is, can Terraform interrogate a host to see how many CPUs it has and then turn that into a variable and apply that to another resource?
No, it doesn't have any interrogation kind of stuff, unfortunately. Because it causes, the problem is at the planning step, you want to be able to say, this is what I'm going to do. Right now, today it can't, but it has a pretty generic hook system built in. So there's ways of basically adding separate hooks, so you could add your own like quota logic, where it'll go and be like, hey, I'm about to boot 50 web nodes, is that okay? And then the hook could be like, no, that's way over budget, and Terraform will just like blow up and be like, nope, the hook said no. So there's ways, we're planning on ways where you can integrate that kind of business logic, but it's not currently a part of the core. But the mechanisms are in place to do that kind of enforcement. Mhm. The problem is the examples become pretty big, right? You end up with a lot of resources, so it becomes not something you fit on a slide. We have some online. So go to the Terraform website, and it's under like the intro thing, and then there's like the more realistic examples section or something. And there's like 4 or 5 that do a larger scale one. I think there's one that's like a blog post on how to deploy like a 4-tier discourse like blog thing. So there's one of those that gives you a more real world, okay, this is what it looks like when it's not just 2 resources kind of a thing. And then I think we actually, well, maybe we published it, but Consoles Cluster, which does a multi-region console cluster deploy, that one's actually all orchestrated with Terraform too. And that one's DigitalOcean and some CDN and a DNS provider things layered together. So that one is a real world example too. And I think checked into the console GitHub, I think it's in there. If not, just like send me an email and I have it somewhere. Oh, sorry. I'll get him and then I'll get you. Mhm. Yeah, so you can kind of abuse the tainting system to do this. So as part of the provisioning cycle, let's say you run like a stress test against it. So you do stress test its disk, you're like, this is below 10, I'm gonna return an exit code for my provisioner. Terraform's like, oh, this provisioner returned an error back. I'm gonna taint this resource. So then on the next cycle, it'll do the destroy recreate basically for you. So you can kind of, you push that testing into kind of a provisioner, and then Terraform will just manage the taint life cycle for you. Ooh, that's a good question. I don't know. I don't know what the scale points are on this thing. I can't answer off the top of my head. I can't give you a good answer. So the community involvement is anytime you run into a provider and you're like, this doesn't fit into the Terraform world, let us know so that we can get that in that world, or even better, add a pull request for it. In terms of what's coming, 0.3 is the big one we've been working pretty hard on. So it brings a lot of improvements in kind of the graph representation, the state file representation, lots of bug fixes. I think a few new providers. I think OpenStack is on the horizon. CloudStack is also on the horizon. The remote state storage migration module systems are coming. So there's a lot of stuff coming down the pipeline right now. We want to do a little better job around things like parallel deploy. So I don't remember who asked. Someone was like, if dev and ops are deploying at the same time, how do you make sure these things are done safely and the state is updated correctly? There's stuff around that. So it's mostly like core is kind of able to move at a separate pace from the providers are. So provider side, we just want support for everything. So that's easy. As long as the core maintains the same API, we can just keep adding more providers to it. And then core, we're just trying to make it better, faster, stronger, so to speak. Mm-hmm. Oh, I see what you're saying. I see. Like a more interactive workflow? We don't currently, but based on the way providers are written, it's something we could add. So maybe a good thing to talk to Mitchell about, actually. He's more intimately familiar. So they use a self-describing kind of a schema. So there's like these helper libraries that help do most of the heavy lifting for the providers. So in theory, it's possible to interrogate the schema and just be like, what is the schema for this resource? And it'll be like, oh, well, I'm going to give you an IPv4 and an IPv6 address and like whether or not you're in a VPC. So theoretically, the schema knows this, and we could build some kind of interaction to let you query it. Because it's in there, it's codified. It's just not exposed other than the documentation.
So you're talking about like dev and ops and deploying at the same time. Have you thought about something like a Terraform master type thing, just kind of like Jenkins, where it's like the state files all there with like an interstacy front end, stuff like that?
Yeah, we've thought about it. We're just not quite there with that. There's enough work that has to happen on kind of the provider and core side that we're just not quite there. But yeah, it would be awesome to have. Cool, awesome. Well, thanks a lot, guys.
Thanks, Ramon. Appreciate you coming out and delivering that. You're welcome to hang out here with us and have another drink if you'd like. Chat some more with the guys. And thanks, Mitchell, as well, for popping in as a guest. We appreciate it as well. So with that, that's it for the night. So thank you.